Modern architecture relies on a bizarre contradiction. We build towering, 1,000-foot vertical shields using silicate glass, a material defined by its inherent brittleness. These facades face severe continuous loads. At extreme altitudes, a building is constantly battered by high-velocity atmospheric wind pressure, causing the entire structure to physically sway. Simultaneously, the glass undergoes massive thermal expansion. The exterior absorbs intense solar radiation, while the interior is regulated by commercial HVAC cooling systems, creating a steep temperature delta across a few millimeters of material. To survive these chaotic environmental forces, you might assume the glass itself must be heavily stiffened, relying on absolute rigidity to hold its shape. But rigidity is exactly what causes brittle materials to shatter. Instead, a skyscraper's structural integrity comes from a precisely engineered state of continuous internal stress. Through a specific sequence of thermal and chemical interventions, engineers trap the glass in a permanent mechanical battle, forcing its outer layers to compress inward while the core pulls outward. The monolith's survival depends on calculating and deploying these internal mechanical stresses to neutralize external atmospheric loads. To understand why this internal battle is necessary, we have to look at untreated, annealed silica glass. In its baseline state, its atomic lattice is a disorganized network of silicon and oxygen. When you apply a pure compressive load, pushing the atoms closer together, this lattice is actually highly stable. Glass can support a massive amount of physical weight if it is simply being squeezed. The vulnerability emerges when the material bends. When a strong gust of wind hits a flat pane of glass, the center of the pane bows inward. In this 2D cross-section, the inside curve compresses, but the outer convex edge stretches, applying a heavy tensile load. Every glass pane contains microscopic manufacturing scratches. When the surface stretches, these tiny flaws act as stress concentrators. Tension pulls the flaw open, immediately severing adjacent atomic bonds. A crack propagates through the entire lattice at thousands of meters per second. To prevent this catastrophic failure, engineers must ensure that the surface layer never experiences tension in the first place. The solution lies in preloading the material. Before leaving the factory, the glass is subjected to forces that program a permanent stress state into it. Because engineers know the environmental forces a facade will face, they can calculate the exact mathematical inverse of those loads and build that opposing force directly into the pane. The required equilibrium demands two distinct zones. First, the vulnerable outer layers of the glass must be placed under a state of continuous compression. This gradient shows the target equilibrium. To balance compressed outer layers, the internal core must hold opposing tensile stress, constantly trying to shrink. This pull fights the rigid outer layers, acting like a tightly wound spring, locking the exterior into permanent compression. This balanced tension gradient keeps the surface squeezed tightly together. Any microscopic cracks are mechanically clamped shut before an exterior wind load can attempt to stretch them open. Building this gradient requires manipulating the glass at the macroscopic level using thermal quenching. The process begins by heating the raw silica pane to roughly 620 degrees Celsius, pushing it just past its transition temperature. At this heat, the atomic bonds loosen. The glass is no longer a rigid solid. It becomes a viscous, expanded structure. High-pressure cooling jets blast the exterior of the hot glass, instantly solidifying the outer geometry. The insulated core remains hot. As it finally cools and shrinks, the trapped core pulls the frozen outer layers inward, generating permanent surface compression. This macroscopic thermal quenching establishes the baseline gradient, forcing surface flaws shut to prevent failure under standard wind loads. While thermal quenching provides deep structural protection, it lacks the surface density required to withstand high-velocity point impacts or hyperfocused bending. To reinforce the surface without disrupting the core, engineers apply a secondary chemical intervention, the ion exchange matrix. The thermally quenched glass is fully submerged into a molten salt bath. This bath consists of a potassium-based molten solution, heated to roughly 400 degrees Celsius. The heat is strictly controlled to avoid erasing the thermal gradient. The objective is to alter the atomic lattice only at the outermost microscopic layer. At the lattice edge, small native sodium ions vibrate, detach, and diffuse into the bath. Larger potassium ions immediately force their way into the vacant gaps. Being too large, they tightly pack the surface lattice. This atomic crowding creates a highly compressed exterior skin. By deliberately wedging larger ions into the surface, engineers increase the magnitude of the local compressive stress tensor, creating a reinforced microscopic boundary. Stepping back from the microscopic lattice, we can evaluate the completed monolith as it faces extreme altitude loads. This bimodal stress profile reveals the exact engineering. We have the deep parabola of compression provided by thermal quenching, now capped on both ends by the extreme compression spikes from the chemical ion exchange. When high-altitude atmospheric wind pressure strikes, it hits this combined defense. The wind induces a severe inward bending force across the span of the glass structure. Zooming in on the convex exterior layer, where a stretching forces peak, we can observe the conflict between the wind vector and the built-in compression. The environmental tension cannot immediately stretch the glass. It must first work to subtract from the preloaded compression built into the surface. The wind force is absorbed before the net surface stress drops to zero. Even under load, the glass remains in the compressive zone, preventing the tension that would lead to failure. The monolithic crystalline shield survives high-altitude forces by ensuring its internal compressive preload exceeds the predicted external tensile loads, keeping microcracks from propagating.